Yeah, okay. So, uh, yeah, so we were doing this LTL to GNBW um, translation. So what we essentially mentioned is like uh, given an LTL formula, you can construct a GNBW which accepts the same language as the set of words which satisfy the formula file. Right? And what we saw is that the size of this GNBW is exponential in the size of the LTL formula. Okay, and yeah, we essentially went over the construction in detail, and we also showed the proof of correctness of the construction in the sense that the language which is accepted by this automaton is exactly the set of words which satisfy the formula file, right? We showed the inclusion on for both the directions for this, and this is what we were doing in the last couple of lectures, and then uh, yesterday we were also looking at some examples. So for example, if you're given, say, like next of A, then how you can, this is how the corresponding uh, GNBW it looks like, right? So we are using the corresponding GNBW looks like this, and and essentially, right? And if you have A until B, if you have A until B, then this is how we found that the GNBW looks like the corresponding GNBW for A until B. We went over this construction, this example, and we also looked at an example to show that this exponential bound, you cannot somehow, like it's a necessity in the sense that we showed some lower bounds, right? So what we showed is that there exists a family of LTL formulas uh, such that the size of the formula is polynomial in n, and every NBW has a size which is at least exponential. Okay, so this is what we saw yesterday. Okay, so today we will look at the complexity of the satisfiability and the model checking problems. Okay, the LTL satisfiability and LTL model checking problems. Today we start with that. So first, let's look at this lemma which says that the LTL satisfiability problem is in p-space. So first, so what we are going to prove is a p-space completeness for both the problems. So first, let's start with the membership. So which is like the LTL satisfiability problem is in p-space. Now, can you say why is it the case? Why is it the case that the LTL satisfiability problem it's in p-space? Why is it in polynomial space? So why is it the case that it's in polynomial space? So how do we check the satisfiability? Suppose you are given an LTL formula file, you want to check whether it is satisfiable. That means whether there exists a word which satisfies the LTL formula file. So how do you do that?
We can construct the automaton.
We can construct this automaton.
And then check for non-emptiness of the automaton.
Check for the non-emptiness of the automaton, right? With GNBW, correct? And so the size of the automaton is how much? It's exponential. And we are saying that the problem is in p-space. Why is it in p-space? you can do this on the fly construction, right? So essentially, like you have this exponential sized automaton, but you don't need to store the entire automaton. You can just guess. So you can indeed have a non-deterministic polynomial space Turing machine, which will do on the fly, like only the parts which are required. It will guess like essentially a path. It will essentially guess a path, right? Starting from the initial state to the final state of the automaton, path in the automaton, and it will just try to guess that path and construct that path like the edges one after another, and it can do that on the fly. You only need to store, given that there are exponentially many states, you can store each such state, and you also need to store a counter, like to say that you don't, like if you have a path, you can reach one of the final states from an initial state, and then checking all these loops, right? I mean, you can consider this to be an NBW, non-deterministic Bushy-Ward automaton. And you can check like a path from the initial, you can check for a path from an initial state to some good state, and then like you can look for a loop there, right? Which goes through. I mean, it's not a self loop, but there is a cycle essentially, right? So it is like that non-emptiness for non-deterministic Bushy-Ward automaton, right? Non-deterministic NBW automaton, which we found that it is indeed in n-log space. But here, since the automaton is exponential in size, you can do this in p space, right? So it is actually like you have NP space, but then because of Savage's theorem, uh, you can get it in P space, right? So you have an on-the-fly construction. Clear? Any question on this? Okay.
No questions.
What? Sorry, I could not hear you. Could you repeat?
No. I said no questions. That's
Okay. And now the next lemma says that the model checking problem 2 is in P space. So as we did the satisfiability, we found that it's in P space. How can you show that the model checking problem 2 is in P space?
So now we just want to check if the language is contained.
The language is contained, right? So in the model checking problem, what is given? You are given a Kripke structure K, and you are also given an LTL formula phi. You want to verify whether this Kripke structure K, it satisfies the LTL formula phi, right? And this is like you can essentially check whether the language of the Kripke structure it is a subset. It's contained in the language of the corresponding automaton. Right? You can construct an NBW which is exponential in size, and you can check the inclusion, right? And this is true if and only if the language of the Kripke structure intersected with the language of the automaton corresponding to the complement formula, right? If this is empty. And now you can also, so taking this intersection, this is some kind of a product construction you can do, right? You can do some sort of a product construction. You recall like we had NBW and then intersection. If you are taking the intersection of two NBW, you can make those two copies. You remember like there are these two copies. So you can do, it's still polynomial in the size of the input NBW. Now this is this automaton. Now the size of so you were given phi and you were constructing negation of phi, right? And if you check that the size of negation of phi is, let's say it is like the size of phi plus 1. Okay. And another thing to note is that the size of the automaton phi, right? It is the same as the size of the automaton negation of phi. I mean, it's of the same order, right? It's like that you can say. And why is it true?
Because
Because
it's a constant time exponential. Even if you order mod 5 plus 1,
Huh.
which will be just be a constant times.
Yeah, but there is slightly more than that. Like, what is that? Like, so when we constructed the automaton, the states were those elementary states. Like you consider the closure and you had the elementary states. So if you consider the closure of a formula phi and the closure of a formula negation of phi is the same, right? The closure has the same set of
So just
subformulas,
your
right?
start
Yeah.
states and the trans-
Start states and those, yeah, exactly. The accept states will be different, right? So just to recall what we were doing, so we started with the complexity of the satisfiability and the model checking problem, right? This is what we are doing. So we are going to prove that the LTL satisfiability as well as the model checking problem, both of them are p-space complete. We started with first showing that the memberships, so which is like the LTL satisfiability problem is in p-space. And how did we do that? Is like, okay, for satisfiability, you construct the automaton and check for its non-emptiness. And you can, so the automaton is exponential in size. And it's like NBW, if you recall NBW non-emptiness, it's in NL, there's an NL membership. Here it's exponential in size. And hence you get an NP space, but NP space is same as P space by Savage's theorem. So you get a P space membership, right? So this is what we did, and you have essentially this on the fly construction of the automaton. So you don't need to store the entire automaton. You can guess, like there is this non-deterministic polynomial space machine. It can guess a path and the relevant path, and then it can do that computation in polynomial space. Okay, and then we also said similarly like the model checking problem in p-space, because if you are given a Kripke structure and you are checking whether it satisfies a given formula phi, so essentially we are trying to check this, then the language of the Kripke structure is essentially included. The set of all computations of the Kripke structure, it's included in the language of the automaton corresponding to phi, which is like saying that the intersection of this L of k with the automaton corresponding to negation of phi, this is empty. So intersection is like you are doing a product construction, and that's also exponential in size of the input. Like, so this is like the Kripke structure is already like, and in some sense you can consider this, that if the system itself is like an automaton, right? The system model. And so this is linear in the size of the automaton. Like, so what I'm saying is that the k here, the k here is already, it's given, it's linear in the size of the input. And this part, the a of negation of phi, is exponential in the size of the input phi, right? So the total, the intersection is also going to be the intersection automaton. It's going to be linear in the size of k and exponential in the size of phi, right? So it's exponential in the size of the input, but again, then you don't need to construct and store the entire this automaton, which captures the intersection language, but you can again, like a non-deterministic polynomial space machine, it can guess the relevant part and check for the non-emptiness, right? So you again get here an NP space membership, which is the same as a P space membership. Okay, good. So this is what we did. So now we are going to do the hardness, right? So first we'll do that the LTL model checking problem is p-space hard. Okay. So first we will see that this problem of, instead of the standard model checking, there is something called an existential model checking. What is that existential model checking? It says that there exists a path in the Kripke structure, there exists a computation of the Kripke structure which will satisfy the formula phi. In general, when we say that the Kripke structure K satisfies phi, it means like all computations of K should satisfy phi, right? And the existential model checking, it says like, okay, does there exist a path pi which will satisfy phi, okay? And essentially like these two problems, like complexity wise, they're not much different, right? I mean, so why? So I mean, here, for example, you can check, see that if K satisfies phi, right? It's a standard model checking. If and only if for all paths pi, it satisfies pi. Okay. And if and only if it is not the case, that there exists some pi such that pi satisfies negation of phi. Correct? If and only if it is not the case that pi satisfies uh, negation of phi for some path pi. There exists a path pi which satisfies negation of phi. If it's not the case, right? Now, this part, if you look at, I mean, this not of phi, it's also a formula. You can consider this to be a formula psi something, right? It's and and the negation is like, so yeah, I mean, essentially, if you consider this, like if this is like p space hard, then this is p space hard, this is copy space hard, but copy space is again the same as p space, right? So this is the Timmerman isolate from that it appears. So um, so we are essentially going to reduce this problem to this existential a p-space complete problem. So what is the p-space complete problem? The standard p-space complete problem, which is like you have the set of m comma w, this tuple, where m is a Turing machine that accepts a string w using at most uh, these many cells, at most these many cells, at most this much of space, where p is a polynomial of the size of the input string w, right? So this is a canonical p-space complete problem. Okay, it's the language of all these tuples m comma w, where the Turing machine m accepts w in some amount of space which is polynomial in the size of the input string w. Okay, now this is a p-space complete problem, and so this L reduces, will show that L reduces to this problem k psi, where I mean, this problem is essentially some path pi of k satisfies psi. Okay, some path pi of k satisfies psi. So this is the existential model checking problem, and this will show that this problem is p-space hard, and this is equivalent to saying like not all paths pi of k satisfy negation of psi, right? So this is equivalent. And now if you take the complement of that, right? So this is like all paths pi of k satisfy phi. And but okay, so here is a negation. The negation is not there, but you can just construct an instance. Like if you start from an instance k psi, you can get here take here the instance k comma phi, right? So and here we are saying that this is like the negation of this problem, but again, OP space is the same as P space, so everything we are fine with this, right? So this is our standard model checking problem, right? So this gives that this is also P space. Is it okay? Like, so this is the idea. Good. So now let's do this reduction, right? So we are going to reduce this problem to this existential model checking problem, right? So given an m comma w, in order to do the reduction, what do we need to do? If we are given a positive instance of problem 1, we are reducing it to problem 2, we need to get an instance, positive instance of problem 2, right? And so we are given an instance m comma w. We would like to construct what? In this case, for the existential model checking problem, what would we like to construct? K comma phi. We would like to construct a Kripke structure K as well as an LTL formula phi. Clear? Okay, so this is what we would like to do. Okay, so now it's very similar to like the reduction where you might have seen that like SAT is NP complete, like sat is NP hard, right? The Cook-Levin theorem, right? So you essentially encode the run of a Turing machine there, right? So the reduction here is very similar to that. So you have, let's say, I say that gamma is a tape alphabet, and uh, without loss of generality, we can assume that we have some accept states, and once you reach the accept state, you absorb. So you are just like, these are like, once you reach an accept state, you stay there. Okay. So what are we going to do? We were going to encode the run of a Turing machine. So we'll have some initial state of the Turing machine, the initial configuration of the Turing machine, which is like you have essentially like the tape, and the tape content will look like the following, right? Like you have this A0, A1, A2, etc. Maybe some AN, and here you have, then after that you have these blanks and so on, right? And if it's a like you can also have blanks here if you consider a two-sided I mean the two-sided tape. Otherwise you can also consider, like if it's a one-sided tape, you can say that it just starts from here. This is your initial like this, the first tape cell, and here you also have the tape head. There's a tape head, right? Like it's a read-write head, and you also have the initial state. The Turing machine is at the initial state initially, right? So this is what we are talking about. So, okay, there's a small thing here. Maybe I should just say that, okay, when I was writing, I started with A1 instead of A0. Okay, so the index, the starting index is 1. So I have here, and I say it's Q1 instead of Q0. Okay, it's just like I can somehow I started writing like that. Okay, so so what is the initial configuration? Now I'm going to construct a Kripke structure. How does my Kripke structure look like? So I have an initial state, which is like, I call it S. And from S, I have all these different outgoing transitions, outgoing edges, and the labels are of the following form. Like I have for each A, belonging to that gamma, right? I have like a transition to these A1, A2, where A1, A2, these are the letters in the tape alphabet, etc. Right? So suppose there are some n such letters, okay? Right, suppose there are some n such letters, and then I also have this kind of states, Q1, A1, Q1, A2, etc. up to Qm, An. So where there are like m states are there in the Turing machine. Okay, so these are the outgoing transitions, and then again I come back to another state from all of them like this, and from here again I do have the same thing, right? Starting from A1 up to QAM like that. Okay, so what is the idea here? The intuition is that like I am, and okay, and how many such things are there? Like there are, in total I have like this many number of such states. How many such states? Like so this kind of states, there are polynomial, that PW many such states. So essentially it tries to encode the entire configuration. Okay, the idea is to encode the entire configuration. Okay, so at some point of time, suppose if I have, like if I am here at Q1 comma A2, then it denotes that for this particular tape cell, like it's like this is tape cell 1, tape cell 2, cell 3, like this up to cell this thing, cell polynomial this of this length of W. And if I have, for example, for cell I, if I consider this, suppose some QI AJ, that means that on this, suppose suppose some cell R, if I have this, suppose at the RH cell here, some RH cell here, if I consider this QIAJ, it means that the tape head is on the RH cell and the state is at this point, it's the QIH state, and the content of that cell is content of the RH cell is the letter AJ. Okay, that's the intuition. That's the idea.
So
Okay.
what if it's looks like the head most people have?
Well, yeah, so I'll come to that. So essentially, like we have to encode the transition. We'll start with the initial configuration. We'll also have to encode the transitions, and then we'll say that at some point of time, you are going to accept. Okay, so this is like a run of the Turing machine, which we are going to encode. Okay, and for every such these different things like that, there's an initial configuration, then the tape head moves to the left or to the right. We are going to have corresponding formulas, and we'll take the conjunction of all these formulas to get the final formula. Okay, and this is how the Kripke structure looks like. Okay, and we are going to construct the formula file. Right. So how does the initial configuration look like? So if I'm here, like at the initial state, I'll say at the next state, I should be at state Q1. Okay, my tape head should be at the very first position, and the corresponding state is the initial state, which is Q1 initial state of the Turing machine, and I have A1 here corresponding to this, right? A1, and for the remaining this W, like suppose W is I don't suppose, just to say this is M, for the remaining M minus 1 such positions of the tape, I should also have this corresponding thing, like, so for I belonging to this set. So when I say this is like I from 1 to up to W minus 1 in this set, right? For I belonging to this set, for each such I should see here the W, the corresponding W1. Okay, so this is like I should see the A2 here, then I should see the A3 here in the next one, and so on, right? For how many such things? For the corresponding to the length of the input stream, right? And for the remaining tape cells, because you have polynomially many such polynomial in the size of the input stream, right? This is the amount of tape cells that you have, number of tape cells. And for the remaining ones, you have the blank symbol. Clear? That is the idea. So this is exactly what we are doing, right? And here you see, I am having this x 2i plus 1, right? Why am I having the 2i? Because I'm coming here and then again I'm going here. So it's like multiplying by 2, right? In the Kripke structure. Is it clear? The initial configuration for the online participants, is that any question for the encoding of the initial for the
Yes.
configuration? Yes.
Yeah, I think I'm getting the construction, but I have one question. So,
Yeah.
uh, the the number of blank symbols that
Correct.
can be only finite.
That is only finite. Yes.
Yes. But in general, the Turing machine can have infinite number of
In
blank
general,
symbols, right?
Turing machine can have infinite number of blank symbols, but here we are talking about a piece-based Turing machine, right? A
Oh,
polynomial
right,
Turing
right.
machine where the
Mhm.
size of the tape cell is restricted,
Yes.
that you can only use those many
Uh,
number of, like polynomially many number of tape cells. So you don't need to look at the
uh,
other tape cells. They
right.
are as if like they're non-existent.
Right.
Okay.
Okay. Yes, right. Yes. Mhm. So so is it happening like this? So once one of the configuration is being visited, like Q1, A1, then A2, A3, A4, and then some blank symbols, then it
Hmm.
is coming back again to the start state, and then it is reading something else.
Yeah, I mean, when you are saying that it is coming back, Essentially, if I understand you correctly, what we are trying to do is like we are going from one configuration to another configuration.
Another convert. Exactly.
Right?
Yes.
And this second configuration you will reach from the first configuration by a movement of the tape head, right? A transition you do and you go from configuration, say, configuration L to configuration L plus 1. Okay.
Sorry. Yes.
Okay. So yeah, let's see that. I think this will become clear. Right.
Okay. Okay. Okay.
And
Sure.
then I also want to say that the tape head is on a unique cell, right? The tape head, if you have the entire tape head, so the entire tape, the tape head is on just one cell. You cannot have the tape head on multiple cells, right? So how do you encode that? What is the idea? How do you encode that? Like, so essentially when I'm saying that this Q, like at the Rth tape cell, you have a QIAJ, right? QIAJ. It denotes that on the Rth cell, you have the tape head and the state is QI and the content, the tape content at the Rth cell is AJ, right? This is what we are saying. Now, all I want to say among all these tape cells, there is only one position which is of the form Q, comma A. The remaining positions are just of the form either A or blank, some A or blank, right? This is what we are trying to say, right? So the first, so it says that it is always the case that if I mean, given that like starting from the initial state, I'm satisfying these two kind of constraints. So the first constraint says that there should exist such a QA such a QA should hold true. Okay, for one of the tape cells, the QA should hold true. Okay, and the second one essentially says that for none of the other ones, like for if there is for cell I QA holds true, then for every j which is not the same as I, the QA should not hold true. This is what it says. Exactly. This is what this formula essentially says. So you can just take a look at it. There may be some small errors here and there, but like that is the idea. Maybe if you like, okay, so we are saying that there should exist some I such that, and there should exist some Q and an A such that like that after that 2I minus 1 such states, right, I should be able to see the Q comma A. And this one says that if this is the case at the ith cell I see after 2I minus 1 states I see the Q comma A, then for all j which are not the same as A, it should not be the case that I should have such a Q comma A, right? This is what it's, yeah. So now coming to your question, like the next thing is that how do you encode a transition, right? So I have just shown it for such a thing where the tape head moves to the left. You can also do something similar where the tape head is moving to the right, okay? So what is the idea is that like, so if the tape head is moving to the left, then suppose you have something like this. So there is a cell where you have a C, and then there is this thing where there is an A and the tape head is there, and the cell is Q, right? And this particular transition says that now I am right. So what does it say? That the tape head is on a particular cell which has A and the state is Q, and now there is a transition such that the state changes from Q to Q prime and the A changes to B, and the tape head moves to the left, right? So this is the standard Turing machine, like the way you describe transitions, right? So now if that is the case, then what will you have? You will have C here, there's a Q prime here, and the A will change to B, correct? And all the remaining cells, every other cells, they will remain the same. Everything else, they remain the same. Correct? So this is what we would like to do. So one thing is that we would like to say that this thing got changed. A changed to B. The tape head moved from Q to Q prime, which is on the left, and then the other cells remain unchanged. So for the first part where A is changing to B, so this is what we have. Like, so if it is the case that at tape cell I you have C and the next thing is Q comma A, right? Next means like after two states, right? You have Q comma A. Then when you like for the next configuration, and the next configuration is modeled by like you are coming back to the start state, and again you are looking at this ith cell. Okay, so what is happening there? So I just add that this polynomial 2 times this p of the step size, right? Plus 2i minus 1. So there, so it's like a, so what are we doing? We are doing a we are looking at a computation of the Kripke structure, right? We are looking at a computation of the Kripke structure. So one configuration is of 2i minus, 2 times the tape cell is the size of one configuration, 2 times the tape cell, right? And then the next configuration, like, so I have the computation. So the computation will continue to the next configuration, which will be after that much, 2 times the tape length, right? So that's why I have this 2 times this tape length plus 2i minus 1. So again, I'm looking at the ith cell. So now this thing became the computation. I'll have the q prime comma c, right? So I have such an execution. I have such an execution of the Kripke structure. And then after two steps, then I have B instead of A. Now I have B. Okay. And then I also need to say that the other cells remain unchanged. The other cells remain unchanged. So it just says that for everything else, if it is the case that whenever it is the case that you have a C, but the next cell is not of the form QA, right? If it is not, so there is a step cell. So suppose it's just you have a C and you have just an A. It's not of the form Q comma, right? They will remain unchanged. Okay, they will remain unchanged. This is what it says. If this is the case, then this C remains the same. Like we are not changing the C. Okay. So that's the thing. And now we are saying that we have a formula phi delta, which is a conjunction over all such transitions of the form. Like we just talked about one such transition. You have multiple transitions. So corresponding to every transition, you have such formulas, phi 1 L, phi 2 L, and then you take conjunction over all such formulas and you get phi delta. Clear? And now I also have something called a phi accept, which is like the final state, right? You reach, which says that eventually I would like to reach a state Q where Q is a final state. Clear? So this is what my phi accept say. Disjunction over Q belonging to F. Here the F is actually, sorry, for my, so there is an overloading of the notation. If by this F, I mean a set of final states of the Turing machine, and this F, I mean the LTL eventuality F. Okay, so sorry about the confusion, but I think okay, I hope it's clear. And now I'm saying that this is the final formula. You have phi of W, which is the conjunction of all these formulas, right? Which is that initial constraint, then you have that the head should be only at a unique position, and then this is corresponding to all the transitions, and then finally you have, and you are going to an accept state, right? So this is my final formula, the phi that we are trying to construct. So we already have the Kripke structure. So this is the Kripke structure K. So if you recall, so inside we need to construct two things, the K and the phi. So we already have the K, and now we also have the phi, right? So we have these two things. So Now what it says that now you see that the size of the k and this phi w that we have, these are polynomial in the size of the input word w and the Turing machine name. Okay. Now, and we see that there exists a computation of that Kripke structure satisfying this formula phi if and only if m accepts phi. Okay, if and only if m accepts phi. Clear? Okay, right. So that's the thing. And now, hence, what it leads to is that the existential model checking problem is piecewise hard. Okay. So that given that the existential model checking is piecewise hard, it also shows that the model checking problem for LTL is piecewise hard, which we started with showing that yeah, they are kind of have the same complexity, the existential model checking problem and the piecewise models. Sorry, the standard model checking problem, right? So this this is the reduction. Okay. So any question? No? No, good. So for the online participants, any question do you have? No? Okay.
No, it's clear. Yeah.
Okay, good. So now we did the complexity of the model checking problem, right? So we also want to do the complexity of the satisfiability problem. So we saw that we saw the membership of both the problems, that both of them are in P space. We would like to now say that indeed the satisfiability problem is also P space hard. And how do we do that? We indeed reduce the model checking problem that we saw to non-satisfiability, right? So the non-satisfiability, we saw that the model checking problem is piecewise hard, so the non-satisfiability will also become piecewise hard. Hence the satisfiability is co-piecewise hard, but since co-piecewise is the same as piecewise, so we'll also have that this is piecewise hard. Okay, so that's the idea. So now what do we do? So we are given a Kripke structure here. So we are reducing from the model checking problem to the satisfiability problem. And we are given a formula phi over the set AP of atomic propositions. We are constructing an LTL formula phi. Okay. We are constructing an LTL formula phi. Or let's say we are constructing an LTL. So I'm using phi here. So that's why I write psi here. So we are constructing an LTL formula psi over the set of atomic propositions and W. What is W? W is this, the set of worlds in the Kripke structure. Such that K satisfies phi, K satisfies phi, if and only if psi is unsatisfiable. K satisfies phi, if and only if psi is unsatisfiable. Right? So, right. So, right. So let's see how do we do the, again, the reduction is quite simple. So what do we do? So we would like to first encode a run of the Kripke structure. Okay, we will have a run of the Kripke structure which does not satisfy phi. A run of the Kripke structure which does not satisfy phi. Right? So if there exists such a run of the Kripke structure which does not satisfy phi, that means that the Kripke structure K does not satisfy, like the model checking does not satisfy the phi, right? I mean, the model checking problem is like whether K satisfies phi, right? If it happens that there exists some computation, there exists some pi of the computation of the Kripke structure K such that indeed pi does not satisfy phi. Oh, okay. So that means, so it essentially implies that K does not satisfy phi, right? So this is the thing, right? So let's see what we want to say. So again, we are trying to encode a run, such a run of the Kripke structure which does not satisfy phi. Okay. So how do we encode a run? You have the initial state and then you have the transition relation. So you want to say that I am here and in the next step, I'm going to be in one of the successors, right? Like that. So in order to do that, how do I say like initial state is like, let's say, S belonging to W0, and I'll say this S, right? Because if you recall, my formula that I'm going to construct, it is over that AP. This AP is coming from the formula phi over the set AP, right? And uh, this formula psi is over AP and the W, right? So this W is okay. So I'm saying that the initial states, I'm encoding the run. So the initial state is of this form, disjunction over the set of states. And then I also want to talk about a valid run of K, right? So how do I talk about a valid run? So this is like globally, I'll say for all S belonging to W, S implies say S prime, right? Next S prime over this thing, right? For all S prime. So if I'm at S, I'll go to some S prime such that there is a transition from S to S prime. Okay, so this is the thing. And now I also want to say that the atomic propositions, I mean, this is when I'm having the run, it's kind of a consistent with respect to all the atomic propositions, right? So what are these? What does it indeed say? It says that globally it is for S belonging to W, S implies that I have P where P belongs to this L of S, right? You remember that this is the labeling function, right? What does the labeling function do? For every state, it gives you the set of atomic propositions which hold true there. And it is negation of P for P not in LS. Okay, so this is the formula. Okay, so I call them this corresponding this formula. I call them phi 1, phi 2, phi 3. Okay, and now if I see that phi 1 and phi 2 and phi 3, it gives the description of an infinite path of K, right? Phi 1 and phi 2 and phi 3, it gives the description of an infinite path of K. And now if I say, consider this formula, phi 1 and phi 2 and phi 3 and negation of phi. Okay. Now, what can I say about this formula, phi 1 and phi 2 and phi 3 and negation of phi? When will this be satisfiable? When will this be satisfiable? When will this formula be satisfiable? Like phi 1 and phi 2 and phi 3, this gives the description of an infinite path of cover. Yeah.
There exists an infinite path which doesn't satisfy it.
Exactly. Right. So this is, you say that this is satisfiable. This formula psi, it's satisfiable if and only if the computation, okay, the computation of this path of infinite path, let's say pi, computation of pi does not satisfy phi, right? So essentially I'm talking about an infinite path, right? So this is some infinite path. You see that there is a disjunction here. So I have different possibilities, like I'm talking about some infinite path, and that infinite path should not satisfy phi, right? So this is the formula. So this is satisfiable if and only if there exists some infinite path, right? Why I said exists, because there is a disjunction here. You talk about some, like this formula will be satisfiable if there exists some infinite path along which this formula phi is not satisfiable. Now you see that phi is over the set of atomic propositions AP. Okay, and here you are getting that set of atomic propositions from these parts, right? These things give you those atomic propositions from AP. right? And this essentially, like if this is satisfiable, means that the computation, there exists some computation of pi which does not satisfy phi, right? And that is the case, if and only if k does not satisfy phi, right? By definition, correct? There exists some path computation which is not satisfying phi. It means that k does not satisfy phi, right? Because when I say k satisfies phi, it means that all the computations of the Kripke structure should satisfy phi, right? So there is an implicit for all quantification there, right? So then what do we get? Right? So yeah, um, right. Um, right. So we get this, right? That this formula psi is satisfiable if and only if k does not satisfy phi, right? So hence satisfiability, right? So given, so what was the, how does the reduction work? Like given k comma phi, we constructed psi. Given k comma phi, so this is from the model checking. It's an instance of the model checking problem, and this is an instance of the that satisfiability problem, right? Satisfiability, right? It's actually the not the model checking, like the negation of that, the negation, the complement of the model checking. It's a negative instance of the model checking problem, right? And here it's a positive instance of the satisfiability problem, right? So hence the satisfiability problem for LTL is co-p-space hard. Is it clear why it is co-p-space? I am writing why it is co-p-space because I am saying that it does not satisfy phi, and we found that the model checking problem is p-space hard, and so it's co-p-space hard, and hence p-space hard, right? The satisfiability problem is p-space hard. Clear? Okay, good. So thus we finally get this, that the LTL model checking and the satisfiability problems, they are both p-space complete. We showed the we saw the membership problem for both of them earlier, and now we are looking at the hardness, and hence it is space complete. Good. Now we will do something interesting, like something which we have not really done so far. I mean, we have seen earlier also some, I mean, this construction of the automaton correctness, and then complexity, all these things we have done earlier also, right? Like for different kinds of things, like when we did from MSO to automata construction, we looked at those kind of things. But now what we are going to look at is about the expressive power of LTL, right? Expressive power of LTL. So what have we seen? That if we are given an LTL formula, you can translate it to an NBW. This is what we have seen. A GNBW, which is again the same as an NBW. Now, so what can we say? That every LTL formula, the language corresponding to every LTL formula, this is omega regular. We can say that, right? So, given phi, we know that L of phi is omega regular, right? This is something we know. What about the other direction? Is every omega regular language, can that also be expressed using an LTL formula?
No.
No. Oh, why do you say so?
Uh, Thinking something like parity, like every even position has a
Huh.
or something like that will not be expressible.
Something like that will not be.
LTL expression.
something like that will not be expressible in LTL. Okay. Yeah, you are right. So, and do you have an intuition as to why it is the case?
Because with Bookie Automata, we can quantify over sets of positions, but here there is no such
Okay.
concept.
Okay. Okay. So so yeah, this is what we are going to see now. That indeed, like LTL, it forms a strict subclass of the omega regular languages. So in fact, there are languages which are omega regular, but you cannot express them using LTL. And we are going to see such a characterization, like what LTL can do. I mean, not exactly a characterization, but in some like how much LTL can do. So we are going to look at some subset of omega regular languages, and we'll say that LTL can do only that much, and there are languages which are outside that class. Okay. So we are going to define something called non-counting languages. Okay, we're called non-counting languages. So the idea is that, like, so what is so we will show that there are languages which are omega regular but cannot be expressed using LTL. But when are we looking at these logics, right? Like we have looked at some other logics also, MSO and LTL. So there should be other questions also which should come to your mind, like, right, about expressiveness and things like that, right? So anyway, so right now we are only talking about this omega regular languages and LTL. And when you talk about the non-counting languages, so we say that a language, right, a language is non-counting if there exists some natural number n0, there exists n0 such that for every n greater than equal to n0 and for every uv which belongs to sigma star, right? So, and x belonging to sigma omega, we have, so I'll say a language L, let's say a language L is not counting. We have that, we have UVN, right? What is n again? So there exists some n0 such that for every n greater than equal to n0, and again for every UV for every x. UV are finite strings, x is an infinite string. Okay. We have that UVN belongs to L if and only if UVN plus 1, sorry, x belongs to L. Okay, so let's look at the statement again. So what are we saying? So the language is non-counting. A language is non-counting if there exists some n0, if there exists some n0, such that for all n, for all natural numbers which are greater than equal to n0, and for all uv, which are finite strings, and for all x, which is an infinite string, you have that uvn x. So v is pumped. V is an infix, a finite infix, which is pumped n times. If that belongs to L, then if you pump V again, it will still belong to L, right? For every such n, this is the case. So it means that non-counting means that if you pump an infix, like the intuition is that if you pump an infix string some sufficient number of times, then it does not matter. So this is just an intuition. This does not matter how many times we have really pumped it. How many times we have pumped it. Okay. How many times it has been repeated, right? It does not really matter. So that's the thing. Okay. Is the statement clear? Is the definition of the non-counting language clear? So now let's look at some examples. So what about this language? The language of a set of words where they have infinitely many ones. Say, let's say the sigma is 0, 1. Is it non-counting or is it not non-counting or counting?
It is not,
It is non-counting. Why do you think so?
but even if we pump the infix one more time,
What is the infix like? Or okay, maybe sorry. Go ahead.
like, suppose we have a word W, and we split it as U, V, and X.
X, yes.
And if we pump the V one more time, still it's some finite substance, so whether there are infinitely many ones or not is really the same.
Good, very good. So that is what. So essentially, like if you have some UVNX, right? It belongs to L. It all depends on whether this X, then X has infinitely many ones. Many ones, right? It's all about that. Now, if this belongs to L, it does not really matter what you have in the V's, right? So if this is the thing, then this is indeed equivalent to saying UVN plus 1 X belongs to L. Hence, this is the language, this language is non-counting. Clear? Okay, good. Now, what about what about the following language? So here just maybe one thing here, you can use your N0 to be even 0, right? I mean that works, right? Okay. Correct. What about this one?
It is not non-counting.
And why is it so?
If we have something like 0, 0 and then 1 to the omega, and if we take the 0 and 1 as V, and if we pump it W, then the word we get is outside the language.
So if you have V is just a single 0.
No, it's a 0 and 1. So the
But
word
if you have 0 and 1 as V, then it says that. So what is the statement? The statement is the following, right? So there exists some N0 such that for every N belong greater than equal to N0 and for every UV and such X, if this is the case, then this has to be the case. So you have to have this in the language. If this is not in the language, then this is also not in the language. It's an equivalence. Right? Yeah. Now,
But still, this kind of requires you to make sure that the number of zeros are even. So so if you had taken 0 as the V, then you pump it, you can't really say it's going to be even in your.
okay. So the thing is that the quantifiers are really important here. It says that for every UV, right? For every UV, you consider any N0, right? So suppose I'm saying that I'm claiming that this is not a non-counting language. Okay, this is not a non-counting language, right? So it says that that means for every N0, you choose any N0, right? And I should be able to get some N which is greater than N0, such that if it is the case that UV and X belongs to L, then UVN plus 1 X does not belong to L, right? So suppose I say that you choose any N0, and it can happen that 0 you take 2 times n0 times, right? And 1, so my v is, let's say, just a 0, single 0, right? And this of course belongs to L. For every n0 I can get an n, right? So which is equal to, let's say, 2n0. This belongs to L, but 0 2n0 plus 1, right? My n here is 2n0. Sorry, I should have a 1 omega here, and 1 omega, this does not belong to L, right? Correct. And hence, okay, so I'm saying that for every n0 belonging to the set of naturals, we can choose such an n, input. Hence, this language is not non-counting, right? Yeah, but maybe let's say I can talk about one more example. Let's say it might appear later also. So we are left with another 15-20 minutes. I wanted to do the proof of this, but we'll see. What about this one? Is this non-counting or is it not non-counting?
I think it is.
Not
It is not non-counting. That is what you said. Okay, why?
like same reason as above.
You are saying it is non-counting.
Yes, no.
It is non-counting. Okay, why do you think it is non-counting?
Because there the issue was like you can't really distinguish between the 0 at odd position and 0 at even position. But here we don't have such issues.
Yeah, but like as far as the definition of non-counting goes, like so essentially, like what does it say? For all UVx, UV are finite and x is infinite. So you want to say first, if UVn x belongs to L, then you have to have UVn plus 1, right? X belongs to L, right? So there exists some n0 and such that for all n greater than equal to n0, right? This is what we want.
Maybe it is not because if you take V as 0, 1, 0,
V as 0, 1, 0, okay?
then when you pump it, it becomes like 0, 1, 0, 0, 1, 0. So 0, 0 thing is coming.
Sorry. No, but what does it say? The thing is the following, right? Like for every n, if this is the case, UVn x belonging to L implies that this belongs to L and this belonging to L implies this belonging to L.
So I am taking U as 0, 1,
U as 0, 1,
V as
0,
0, 1, 0,
0, 1, 0.
and then X is 1 omega.
X is 1 omega. Okay.
Then UVX is there in L, but UV to the 2.
No, but you must also have to choose an n0, right? There should be some n0.
You choose. Beyond that.
Such that for all n, right? If this is, so first of all, like suppose your V is like this. So this is fine, right? Okay, I have chosen my V to be like this. Now, what do I need to say? like I also need to talk about some NC. Suppose I talk about my N0 is, let's say, 2. Okay. Now I say that what is my UV 2x? What is the form? 0, 1, 0, 1, 0, 0, 1, 0. This is anyway not in L. You repeat, it doesn't matter. It is so it is not, I mean, you could not prove so far that it is not non-counting. Okay.
I think if we take and not equal to 2, then
It should
work.
It should work.
Yeah.
Right. So indeed the thing is that this is in fact it's non-counting. It's in fact non-counting. And you can try to write an LTL formula for this. What should be the LTL formula for this? What should be the LTL formula? Anyone among the online participants also? What should be the LTL formula for this 0, 1 star?
Yeah, I guess we can say the initial positions.
Yeah, the initial position is like you start with a 0. Right?
And then the sub formula will be next one, and we'll have to say an until, after which it will be globally like 1, right? Yeah.
The until part will be like until forever 1. And now we have to decide the part before that. 0.
So 0 should be alternate with a 1, 1 should alternate
Yeah, so
with
0
1.
and
0.
next 1.
Yeah.
1 and 0 until
Somewhere, and then you can say globally 1, right? So try to do it yourself. Should not be too difficult, okay? So try to do it yourself. You should be able to. Can you write a first order logic formula for this? Like we saw that MSO. So do this. Okay, I did not ask you, but this one and this one, do you recall something? Like did we see such things earlier?
That is not definable by, so because of the counting reason.
Which one is not definable by MSO?
0, 0.
It is not definable in MSO.
No, the other one.
This one is not definable in MSO.
No, there was the logic that does not have the counting that cannot define 0, 0 star.
Right, but I'm saying that we also looked at MSO and first order logic over words, right? Do you recall something about when you see this language and this language? Do you recall something? We can try to go back and try to see when we when we see something like this, right? You see that it appears 0, 0 star 1 omega. Okay, and we also had 0, 1 star 1 omega. So we saw this, right? So we saw this. So what did we see here? So when we saw these languages, right? So what was the thing that we
wanted
sort of
the
focused on?
MSO because of 0, 0.
We wanted
the MSO conditions because of 0, 0 star 1.
We
wanted to give the counting because of 0, 0 star 1.
What do you mean by counting? Like in the, so I'm talking about, we looked at this monadic second order logic, right? And then we looked at both, we saw both these examples, 0, 0 star 1 omega as well as 0, 1 star 1 omega. And what did we say about 0, 1 star 1 omega? And what did we say about 0, 0 star 1 omega?
There's a first order logic for the 0, 1 star 1 omega thing.
Yes.
And we need second order logic for 0, 0 star.
Yes. Okay. So we said that this one was like you could express with a first order logic formula. This is like the first order logic formula. And here we say that you need to take care of those even positions and so on. Like you have the capital X to denote the set of event positions, right? And you needed those second order variables, right? So it was an MSO formula. This was a first order logic formula, right? And now we are saying that if you talk about LTL, you can also express this language with LTL. Okay, so there is something called Camp's theorem. I'll just maybe write it. Okay, so we were here. So there is something called a Camp's theorem. Okay, you should. We will not study this really, but you should try to figure out what this is about. Huh? So what is this Camp's theorem? Okay, good. Now, how much time we have? Like 10 minutes. Yeah, 5 to 10 minutes. So we'll now try to prove that every LTL definable language is non-counting. Every LTL definable language is non-counting. And so how do we prove? Like whenever you are going to talk about, like when I say LTL definable language, it means that given an LTL formula phi, you consider the set words of phi, right? And this language words of phi, right? Like LTL formula phi, this is LTL, and we are saying words of phi, right? And this is non-counting. This is what we would like to prove, right? And like any other such proofs, we are going to use structural induction on the formula phi, right? So we'll start with the base cases and then we'll look at the other thing. So suppose let's do the trivial cases and then we will stop. So suppose phi is true, okay? So then what happens? Like you have just, I'm not writing all the quantifications, but you have u, v, n, x, any word satisfies true, right? It satisfies true. U, v, n plus 1, x would also satisfy true, right? So I think this is fine, right? If and only if it holds true. Any word satisfies true, so this is a great. What about if phi equals P, where P belongs to the set of atomic propositions, right? So what about this?
So the first character should have P in it, and that is contained in U, which we are not disturbing.
But U could have been epsilon as well, right? So you can have two cases here. So you can have two cases. Huh? So one is U equal to epsilon, and the other case is U not equal to epsilon, right? The other joke. And then you can observe U equal to epsilon. Yeah. So if U is not equal to epsilon, then you have the V, right?
So
If
then
we-
we just say N naught is 2 or something.
Sorry.
If we say N naught equals 2,
Huh.
then if P is in the first V, then it's going to be satisfying V bar N next and V bar N plus 1 x.
Sure, right? So that is also trivial. So if U is not epsilon, then you just have to check if the V1, the first letter of V, if this equals P, right? That is all. If this is the case, then you have like, sorry, if U not equal to epsilon, sorry, if this, then it is clear. If U not equal to epsilon, then of course this belongs to L if and only if UV. This is trivial, correct? This is trivial. And if U equals epsilon, then all you need to look at is like the first element of V, right? And if V is also epsilon, then it's all about the X, right? And I mean, so you can look at all the cases. I mean, I think it's trivial enough, right? I mean, we are convinced. Okay. What about, so let me know if there are questions, but I think since this kind of trivial, I'm not writing the details, but I think, what about phi 1 or phi? What about phi 1 or phi 2?
So if UV and X satisfies phi 1 or phi 2, then it
Oh.
satisfies.
You are right. So I think just one thing we would like to say, suppose we talk about thresholds here, like the threshold n0, similarly for phi 1 and phi 2, we'll talk about thresholds n1 and n2. For phi 1 and phi 2 respectively. And how do I define n0? N0 is the max of n1 comma n2, right? So now you just say that if you say u v n x belongs to L of phi, if and only if u v n x belongs to L of phi 1 or union L of phi 2, right? And by uh, by induction, like by induction, structural induction, you have. So essentially, it is like you. And it. Okay, let me just write it like this. Or Vn x belongs to L of phi 2. It's like saying, which is if and only if u Vn plus 1 x belongs to L of phi 1 or u v n plus 1 x belongs to L of phi 2, and you can say that if and only if u v n plus 1 x belongs to L of phi 1 and L of phi 2, x belongs to L of phi 1 union phi 2. Right? So this is, I think, clear. Okay. So what about negation?
Since it's if I have lived in the same and not in the
Yeah. So I can again just say, so suppose let n0 be the threshold. Okay, so now I say u vn x belongs to L of phi if and only if u vn x does not belong to L of psi, right? And by structural induction, you have
does not and this when X does not belong to X side.
L of psi if and only if
If U V and X belongs to L of phi.
good. So we are done. Okay. What about x of psi?
And then we'll have to see the cases U is epsilon or non epsilon.
True. Okay. So just to sort of like make those so many cases, like you can have u epsilon or v, like if u is epsilon, u is not epsilon, and things like that. So we can simplify the cases. I mean, I'll just say how you can do that. So one thing is that, like, we'll see, suppose for psi, the threshold is n0, and for phi, we consider a threshold n0 plus 1. Okay, so we see why it is required. I mean, if you just work out, once you start working out, you figure out. But I'm just, since I did that, so I sort of figure out things. Okay, so now you do u v n x belongs to L of phi if and only if I'm just writing this W1 colon. So what is W? So W is W equal to UV. Okay. So that, I mean, I'm just doing this trick so that I don't have to talk about whether U is epsilon and V is non-epsilon and all these kind of things, right? So that's the thing. And of course, if both of them are epsilon, then it's sort of like trivial. I mean, so let's not think about that. So, and 1 colon is like starting from the second position until that entire like the end of the string, right? W is a final string. Yeah. So W V n minus 1 x belongs to L of phi. Okay. So since I'm using this n minus phi 1, so that's why I use this here, that n0 plus 1. Okay. So that's okay. So now you get if and only if you have sorry, not this should be L of psi because I'm starting from the second position. Okay, so what is this x of phi is x of psi. U is uv, so it is like you can write this as u v v n minus 1 x, correct? Now I'm saying that uv is w. Okay, if you and w is like w0 w1 like that, so I'm starting from here w1. So this is what I'm saying, that w1, this part, it satisfies L of psi because I'm starting from the second position, right? So this, if this whole string satisfies phi, then starting from the second position it will satisfy psi. That's what I'm writing here. Clear? Okay, so if and only if. Now by structural induction, what do we have? W1 Vn x L of phi. Okay, and hence if and only if. Now I take the element which I removed in the beginning. So I have UV VNX. I wrote here, there's a typo. Sorry, I think I'm confusing you with the typos. UV VNX belongs to L of phi. Okay, so that is like UV N plus 1x. Is it clear? Sorry for the typos, but if it is not clear, I can go over this again. Is okay? Okay. So any question from the online participants? Any question from the online participants? Is it okay?
No, it makes sense.
Okay, good. So that is this. And so what is left, which is the harder case, which is if phi equal to phi 1 until phi 2. And you can try to do it yourself. And I think, yeah, it's not very difficult, but it's certainly slightly more difficult than the previous cases. And yeah, and I'll stop here and we'll do this last case on Monday. And also on Monday, we'll finish LTL with this thing and we'll start with CTL, which is called like the branching time logic. Okay. Which is a branching time logic. In the sense, the idea is that in linear temporal logic, what happens, like you are looking at time as a line, right? Like as a computation as a single line of different time instances. In branching time logic, we'll think of as if like one particular time point can have many possible successors, right? So you can have something like you have one state, you can have many possible successors. Okay. And we are going to use this logic called CTL. It's more like a tree now. We are going to look at time as like how a system is evolving with time, not over just a single time timeline, but over like different possibilities. So which will you will look now at the time as a tree over all these different possibilities. And this is called, CTL is called computational tree logic. So I said in the last class that LTL, it was introduced in 1977, right? By whom? It was introduced by someone called Amir Mueli. Okay. So yeah, I mean, it's good that you can go and look at least a bit on Wikipedia, like what all things Amir Mueli did, and he received the Turing Award. I don't exactly recall which year, but maybe early 2000, like 2006 or something like that, primarily because of his work on linear temporal logic. Okay, and the CTL. So Amin Weli was in, if I recall, he was in Weizmann in Israel, and then later he was in New York University. And CTL was developed by computational tree logic. It was introduced by Clark and Emerson, right? So Ed Clark and Alan Emerson. Ed Clark and Alan Emerson. I hope I'm writing the spelling correctly. Okay. So Ed Clark and Alan Emerson, and in a slightly different form, I think it was also written, stated by somebody called Joseph Sifakis. Okay. And they went ahead and received Turing Award for their work on computational tree logic, CTL. Okay. So you can also see here about like Ed Clark and Alan Emerson, Joseph Sifakis on Wikipedia. And so we'll start with, once we finish this particular non-counting the expressiveness part, we'll start with this computational tree logic, where you look at time it's like branching time kind of. Okay, so let me end here. Are there any questions before I stop the recording? Okay, so if not, let me